on Monday, December the 7th. Good evening, everyone, and welcome to our webinar this evening on supercomputing and the Argonne Leadership Computing Facility. Our speaker this evening is Michael Papka from Argonne National Laboratory. So this webinar is sponsored and co-hosted by IEEE Chicago section. Also as well, we are partnering together with ACM Chicago as well, and also with the Mid-America Club IT Connect Group and Polymorphic Systems. So we thank you for those from those organizations that are here this evening to listen to the webinar given by Michael Papka. And also, we also want to thank as well the Society of Women Engineers as well for also coming this evening too. So first of all, just a little bit about ACM Chicago, who's one of our co-hosts. So we've done a lot of webinars during this pandemic with IEEE Chicago. So it's been really, really well received. So the ACM Chicago basically is the Chicago chapter of the Association for Computing Machinery. So if you're familiar with IEEE, basically this is similar to IEEE. It's for computing professionals, professional organization. ACM publishes publications, so you can publish in journals, in transactions, in conferences, as well as attend meetups just like this one this evening. So I'm the chair of the ACM Chicago section. And here you can see our website, Meetup, Facebook, Twitter, and LinkedIn to see our previous talks that we've had and also as well for the future talks. So just housekeeping notes, a recording of this talk as well as the slides will be made available after. So we will send an email out to all those who have attended this evening. Also as well, like to thank the members of the Mid-America Club IT Connect. So usually when we have events that are held, actually in spaces or so, we've had some of these events held at the Mid-America Club, which is a private business and social club. So if you know the Aon Center, it's on the 80th floor and it has very, very nice 360-degree panoramic views of the Chicago skyline. And we usually hold monthly meetings on this. And of course, during this pandemic, we've been doing this also online. So Mid-America Club has also partnered together with IEEE and as well as ACM to do these particular types of webinars. So the chair is Vijay and I'm the vice chair. And if you want more information on the Mid-America Club and the services that Mid-America Club provides, they are over there. Okay. And also, I'd like to thank the Society of Women Engineers. So Renee, who is the 2021 president, will be introducing Society of Women Engineers. So Renee, you can say a couple words.
Yeah, so the whole purpose of the Society of Women Engineers is to network with and support women in engineering. And so we do hold professional development events as well as outreach events, and we do have like a membership as well. On the PowerPoint there, you can see our contact information, website, and Facebook.
Great, thank you, Renee, and thank you for your members to attend this evening.
Yeah, looking forward to more collaborations.
Certainly, for sure. Thank you very much. And we have also IEEE Chicago. So I'd like to invite Val Novosad, who is our current chair for 2020 of IEEE Chicago, to say a few words. Yeah, Val? We cannot hear you, Val.
Val, you're muted still.
Is he still muted? Val? Oh, okay, here, sorry. Let me, yeah, here we go. Okay, Val, go ahead.
Hey, can you hear me now?
Yes, go ahead.
All right, so good evening, everyone. Sorry for this technical problem. So welcome to this webinar tonight. It's really a pleasure to see so many people joining in. Just a brief introduction about IEEE. If you're not a member, I would suggest you look at the IEEE.org website. IEEE is the world's largest professional organization centered around engineering in general, and of course, computer engineering including. So it has chapters, sections, and groups of people of interest around the world in 132 countries. So our section here in Chicago is the largest in Midwest, and I'm chairing the section this year. I'm actually from Argonne. I'm senior scientist in material science division at Argonne, so it's especially a pleasure for me to be co-host of this event with Argonne. One thing what I would like to bring attention of people here that IEEE is much interested to promote joint events that kind of along the line of educating people about engineering profession in general, about advances in engineering that exist in our modern world. And so I would like anyone who is interested to work with us together, perhaps next year, to put joint events together, please reach out to us and we'll be happy to work with you. So here you can see some web links to our website and Facebook pages and other social media pages. I hope you will enjoy evening today. It was an interesting lecture from Mike. And Alvin, would you please introduce our speaker?
I will. Thank you very much, Val, for that. Yes, so like Val said, please, join IEEE Chicago. We have lots of different societies to lots of webinars, meetings that you can attend. All right, so of course, the reason why we're all here this evening, right, is to listen to Michael Papka, who is our speaker this evening. So a little bit about himself. He's a senior scientist at Argonne National Laboratory. He also wears a hat of Deputy Associate Laboratory Director for Computing, Environment, and Life Sciences. He's also director of the Argonne Leadership Computing Facility, which he will describe about that this evening. He got his master's and PhD in computer science from University of Chicago. His research interests are in visualization, large-scale data analysis, development and deployment of research infrastructure. He is also a presidential research scholarship and artistry professor at the Department of Computer Science at Northern Illinois University. So certainly many, many distinguished titles for Michael. And here's his email address, papka@anl.gov, if you want to send an email to him. Okay, so without further ado, please give a warm welcome to Michael Papka.
Good evening. Let me see if I can get the screen sharing here to work. All right, everybody can see my slides.
Yes, we do.
All right, let me. So I like the sound of meetup. It sounds much more relaxed than giving a talk. So with that, feel free to, I have the chat window up here if you have questions or that. Along the way, I'm happy to pause and take those. But as Alvin said, I split my time between Argonne National Lab and Northern Illinois University. At Argonne, I do wear a bunch of hats, and that just means that I'm running around like a crazy person most of the time. So, but I spend most of my time directing the Argonne Leadership Computing Facility. And so I'll spend the bulk of the evening describing that and kind of what we have going on there. I see a lot of, I see a lot of names of folks that I recognize in the audience. So this background on Argonne may be overkill, but I think it's worthwhile for us in the audience to introduce it. Argonne is one of the nation's DOE labs. It was founded in 1946, excuse me, as an outgrowth of the Manhattan Project, specifically Enrico Fermi's work at the University of Chicago. It holds the distinction of being the first national lab. So it's the first laboratory to actually get the name National Lab. And its initial mission was to work on peaceful uses of nuclear power. And so over the years, the lab has grown and evolved, and now is a fairly large multi-purpose lab. But one of the things that I like about its history is in the early days, Argonne started building computers and has had computing involved in all the science that has happened there over the years. The lab is grown, as I said. It's about a little over $1 billion research enterprise. It works from the very basic sciences all the way up to the very applied. One of the interesting things about the National Lab System is that it has these user facilities, and these user facilities are a unique asset to the nation. And so the Argonne is no different than other labs in that it has a number of these user facilities, and we'll hear about some of those in a second. And then Argonne's all about collaborating with other national labs, collaborating with universities, and collaborating with industry. The lab itself is about 1,300 science and technology researchers. It supports more than 8,000 users at its facilities. It brings in a large number of visiting researchers. Overall, the lab's just a little over 3,000 employees and a large number of joint faculty members. And I think one of the things that's nice about the national labs too, specifically in the science and engineering space, is it's a very large employer of students. We have a fairly robust summer internship program that I'm even proud to say ran in its entirety last summer. We rapidly converted to online internships, and I think we only, across the lab, only lost like 5 students. We figured out how to do everything else remotely, and so very proud of that fact. As I said, the lab not only works with research organizations, universities, and other labs, but also partners with a number of startups, 2 Fortune 500 companies across a wide variety of sectors, and some of those are represented here. Of course, the lab's real strength is its staff. Over the years, it's won more than 130 R&D 100 awards, had thousands of invention disclosures and patents issued, recognition both nationally and internationally. Last year alone, the lab was a recipient of 2 of the Department of Energy's Secretary Awards, the highest awards that DOE gives. And of course, we have a very proud history of 3 Nobel Prize winners associated with the lab, as well as collaborations with others. The lab itself has grown from those days of studying nuclear reactors, nuclear power, to being multi-purpose. Right now, the lab's focus is on a wide variety of things, but to kind of summarize it up, there are 5 major initiatives that drive the lab's activities. The top 2, X-ray sciences and future of computing, are centered around, as you would guess, 2 of the large user facilities there, the Advanced Photon Source and the Argonne Leadership Computing Facility. Universe as a laboratory really looks at basic science and how our universe, how our place in our universe. This is chemistry and physics and material science. The manufacturing and science engineering efforts are really at leveraging the lab's efforts in other areas and bringing it into an applied space. Argonne is very proud to have been named one of the 5 DOE quantum centers. This was just announced in the last couple of months. Argonne, along with the University of Chicago, leads a center called QNex. We have a number of emerging initiatives. One around looking at cradle to grave, kind of the circular economy. How do things get developed, development of another user facility around radioisotopes. And finally, as we live in this pandemic time, crisis response is turning out to be a lab emerging initiative. And not only in response to the pandemic, which the National Lab has very much stepped up and engaged in use of the advanced photon source and use of computing, but also in just general looking at, other things that the national labs can bring to bear on problems such as understanding the electrical grid and the like. Okay, kind of wrapping up background on the lab is these user facilities. And I think this is something that is often missed when talking about the national lab system, is that it runs a number of these unique instruments. Two of the largest at Argonne are the advanced photon storage, which is a big X-ray source that's in the middle or preparing to be upgraded, become the brightest X-ray source again in the world, in the Argonne Leadership Computing Facility. But we also have ATLAS, which is an accelerator within the nuclear physics group, the Center for Nanoscale Materials, which is co-located with the APS, and you can kind of see it on the back, north right corner of this image here. I don't know if you see that I'm pointing on the screen, that leverages the advanced photon source, but also deploys a number of other instruments in the study of nanoscale materials. And finally, the ARM facility. And Argonne oversees the ARM program in general, and specifically operates the Southern Great Plains. And this is instruments that are collecting all kinds of information about the environment, radars and LIDARs and the like. All right, so enough about the lab. I'd like to spend the rest of the time chatting about the Argonne Leadership Facility. And so what is the ALCF? Well, the ALCF has this mission to provide access to powerful computers for researchers at universities, within the government, or even in industry. But it's a lot more than that. And the one thing that I would say specifically about the ALCF is its dedication to open science. As long as you're doing open science that is appropriate for the resources that I'll talk about today, access to these machines are free. And in addition, access to what I always have to remind myself is the most important thing that makes ALCF great is its staff. And so, not wanting to spend much time on this org chart, just a little bit about the facility itself. It's a little over 100 staff members. At any given time, we have somewhere 10 to 20 postdocs. As I said, we support a large number of students, the bulk of them coming in the summer. Last summer, we had 29 students just in ALCF, about 135 or so across Argonne Computing. And one other thing that I'll point out is we have an operations group that runs the machine. This is something you'd expect to see in a supercomputing center. We have a group that focuses on making sure that those machines run as well as they can. We have a group focused on visualization, data science in support of the users. And then lastly, we have this group of application engineers. And the combination of these three groups really make the ALCF unique. There's a question about, and I'll try to watch the chat and kind of chime in real time on questions. So urgent HPC, I think crisis response would fall into that. When I think of urgent HPC, it's the ability to redirect the resources to a problem that needs their attention right away. Most large computing facilities like ALCF are batch oriented. People submit jobs into queues. Those queues are not friendly to rapid response. And so we could have a whole conversation about how things should change in that direction to be responsive. All right, but yeah, keep the questions coming because I like answering questions. All right, as I said, this is what makes ALCF great. this group of individuals here. We, of course, are a resource provider. We host these large machines for the user community. And we expect our user community to be working on some of the biggest problems in the world that need these things. We have this in-house expertise. And then finally, we have the resources themselves, which are dedicated to open science. This next slide, I could probably spend the whole evening just using this slide here to talk about the ALCF. It encapsulates so many things about the facility in just the one slide. So the ALCF is one half of the Leadership Computing Facility within the Department of Energy's Advanced Scientific Computing Research Area. Its sister facility, Oak Ridge Leadership Computing Facility, is the other half. And a lot of the stuff that I talk about tonight, we do in partnership with Oak Ridge. The Department of Energy also runs NERSC, which is the National Energy Research Scientific Computing. I got that right. And they also run supercomputers for the DOE. And then ESNet, which is the DOE's research backbone. So on this slide here, what's encapsulated here is one of our large computing programs, the InSight program. And I'll say more about this in a bit. The LCFs started in 2004 by an act of Congress. In that first year, they delivered 4.9 million core hours to the user community, and they had 3 projects. So a humble beginning. But what this slide captures is that growth over time. Now this growth comes up and down, and I'll explain a bit why that happens in a second, but you can also see the hours delivered on these machines, growing from that measly 4.9 million to the height of 5.9 billion core hours. And so if your laptop has 4 cores in it, you stay at your laptop and use those 4 cores for an hour, that's 4 core hours of time. So we delivered in 2018 between Argonne and Oak Ridge, almost close to 6 billion. In 2019, we changed our units. It always causes all kinds of reporting nightmares. So we had this rapid drop from 6 billion to 71 million. At this point, we moved to using what we call node hours. They're a little more generic, but they represent what our resources look like now. Argonne has largely been a homogeneous many core facility, but Oak Ridge and even Argonne now have started to move towards these hybrid heterogeneous CPU, GPU based systems. And so the core count drops off there and moves to node hours. The other thing I'd like to point out on this slide is each year, this is what we can deliver to the community. The community asks for more than that. And in the case of the InSight program, 2008 through 2013, the community asked for twice that amount of what we could deliver. Approaching where we're at right now, and we're at 4 times the request than what we can deliver. Lastly on this slide is just the impact of the science that happens on these resources. PhysRev, Science, Nature, the proceedings of the Supercomputing Conference are all premier venues for highlighting scientific activity, and these are routinely put out by these resources. The other thing that I like to point out on this slide too is as you look at these areas in which the publications are occurring, the diversity that's there, from breakthroughs on Parkinson's disease to work on design of reference implementations of concrete to self-lubricating materials to recent award-winning work this past November at SC on accelerating vaccine and drug identification for COVID. So just a huge, huge diversity of activities on these machines. I already kind of mentioned this. You know, of course, we have the machine folks that operate the machines. We have the performance engineering, visualization, data scientists that help ensure that users are getting everything they can out of the resources. We also have this application area, and these are PhD domain scientists who are experts in physics, chemistry, material science, but who are also experts in the resources that we have at our facilities. And in partnership with the ALCF, we help people further their science. And we often see our members of our facility co-authoring papers with our user community. So I'm gonna get to the power in a second. And I'll also get to the visualization resources in a second. All right. So we do run big machines. And the easiest way to kind of talk about the big machines is to actually show a list of them. And so at any one point in time, we have one or two production resources. Our production resource of scale right now is Theta. It's a close to 12 petaflop Intel Knights Landing based system. Again, following that kind of many core architecture, about 300,000 cores in the system. The visualization cluster that backs that up, it helps with the analysis of science done on the machine. Well, there's my friend, so I was just waiting for him to see a delivery or something, so he's been reasonably good. But yep, that's what happens now when we're all home. So anyway, so Cooley is there for doing analysis. It is about 5 years old now and will be retired probably later this summer with a new analysis cluster coming in to replace that. Whenever we deploy a big machine like Theta, we usually try to have a modest sized resource of the same flavor such that we can do software tests in that before messing around with the big machine. So we have a small Intel Cray system called IOTA. We have a bunch of storage associated with Theta, about 18 petabytes of GPFS and Lustre co-located with Theta, and then a global file system behind that of about 50 petabytes. And then we're just getting close to releasing our newest global file system, which is not even listed here on the slide, Eagle and Grand, which are each 100 petabytes. And one of the things I'm most excited about in the Eagle space is it'll be the first production storage system integrated with the facility that has outside sharing. Of course, we have tape robots that back up data long-term. Finally, one of the things that I'm also extremely proud of within the ALCF is the Joint Laboratory for System Evaluation. And we run this in collaboration with our other compute divisions at Argonne. And this allows us to provide a zoo, I guess I could say, of onesie and twosie systems that are the latest and greatest. So we have about 150 nodes of all different flavors in this, ranging from the latest and greatest Intel and AMD chips, power systems from IBM, Marvel's ARM processors, various flavors of GPU systems, tons of different interconnects from InfiniBand to 100 gigabit to Intel's OPA. We experiment with Lustre and GPFS file systems, and including the new Intel Deos system that will file system that will be deployed with Aurora. All at the same time that the group is running these production systems for the nation, for the world, they are also preparing both internal to the facility and our user community for the next systems. And our next system is Aurora. It's expected to be sometime 2022, 2023. It will be based on Intel's upcoming Sapphire Rapids Xeon processors. And more importantly, its computational power will come from the Ponte Vecchio GPUs. Each node will have 2 of those Sapphire Rapids, as well as 6 of the GPUs, again, moving away kind of from the many core to a much more heterogeneous architecture. We expect this machine to sustain more than an exaflop of double precision capabilities. Its interconnect will be based on Cray's slingshot technology, which will be a Dragonfly layout. It will have this Deos file system, Intel's distributed asynchronous object store. It alone will have more than 230 petabytes within that file system, and expected to achieve greater than 25 terabytes per second of throughput. And so we're getting the community ready for this system while deploying those. And then actually today, I'm actually happy to tell you that, not unexpected to us, but probably more unexpected to the community, that this summer we'll deploy Polaris, which will be a 30 to 45 petaflop hybrid system, roughly one CPU to 4 GPUs. This again is to help us get the community ready for Aurora. And so I can't say much about this because we haven't finished signing all our contracts yet, but this probably after the new year, we'll be able to talk more details about what this system has in store. Lastly, kind of continuing on the discussion of resources, it's important to understand that ALCF is a part of DOE's compute infrastructure, compute ecosystem. And this eye chart shows what's on the floor computing for DOE right now in the open science space. ALCF and Theta, which I described. Corey is the large resource at NERSC, and Summit is the top 3 most powerful machines in the world right now at Oak Ridge. More importantly, we can look to the future with Perlmutter, which NERSC will be deploying later this year into next year. Polaris coming at Argonne. This slide's so new, DOE just put this together last month. Turned out some of the information that was on here for Oak Ridge I can't show yet, so I had to black this out, but it will be roughly order of 2 exaflop system, and it's coming later next year in the 22, and then we see the Argonne system. We had the question about megawatts. As you get to the exaflop, they start consuming a lot. We can say that Aurora will be less than 60 megawatts. But I like to actually look at, if you look at something like Theta, while it was considerably lower power than our previous machine, which I'll tell you about in a second, at 15, well, it's 10-ish petaflops for Theta. I forgot to mention, just this last fall in response to COVID, we deployed 24 DGX3s integrated with Theta, which is what takes it to 25.6 petaflops overall performance. And that was really part of the CARES Act. And those resources, up until recently, have been dedicated to COVID research. But if you look at this, is about a 2 megawatt system. When we deploy Polaris, it'll be 3 times more powerful for roughly the same power. So I like to watch those kind of trends as things climb up, and then 5 years later, you see the kind of recovery in terms of energy efficiency. But yes, 60 megawatts is quite a bit. The power use of effectiveness, the ops guys, you have to ask them. I know they have talked to me about this, but I don't recall what it is off the top of my head. The last thing I'll say on the kind of the resources before diving into some of the science that's happening on the machine is these machines kind of become part of your family. And so just this past year, we retired Mira. Mira became online in 2012. We retired officially December 31st of 2019. At DOE's request, and this machine was still running strong, still producing great science. DOE's request, we actually ran it for another quarter, and we focused it on some quantum chromodynamics simulations and they basically ran all out of the machine for for those 3 months. This machine entered the top 500. There's a little list that keeps track of the biggest machines in the world. It entered the top 500 at number 3. It retired into, I think, the mid-20s maybe, still a fast machine in the world. It left as 3rd on the top 500 graph list. This is a list that looks at machines that are very efficient at working on graph type problems. And this is largely due to the interconnect that Mira brought to the table. It had this proprietary 5D Taurus from IBM that was just lightning fast. There was about 800,000 cores in this system. And more impressive, it delivered close to 40 billion core hours of compute to the worldwide community, serving more than 800 projects. And probably the thing that I find the most impressive is it did over 700 full machine runs. This means that a single project, a single user was using all 800,000 cores to work on their science. And it did this more than 700 times. It was a very impressive machine, and we're sorry to have seen it go. It worked from very basic to applied problems. And a lot of the images that you see in the rest of this talk came from that system. All right, I'm trying to watch my time here. All right, so we give out time on the machine in 3 ways. One is through a director's discretionary. I'm going to speed up through for this section here. This is really at getting people onto the machine, get them working on scaling their problems. Sometimes we use this for strategic, maybe urgent HPC allocations. We, of course, have used time in this program for COVID. We've allocated time in the past to the bird flu events. So we use this in a variety of different ways, and this is really at the facility's control. The image we see here is one of some Argonne science. This is a self-healing material simulation, and this was, I think, was calculated on Mira. 2 of the big programs that we give time out on the machine is Insight and ALCC. 60% of the time the machine is available goes to the Insight program. And as you saw in that previous slide, there's only usually on order of 50, 60 at most projects spread across both Argonne and Oak Ridge. And so these are big projects. In kind of core hours, these were hundreds of millions of core hours per project. And I mentioned that they go up and down with time. That's largely to match the deployment of systems. As we deploy a new system, we tend to put more projects on it with smaller allocations, get people used to the system. And then over the aging of it and people get used to the hardware, we put a smaller number of projects for a larger amount of time. And so these are really, Insight is really open to the worldwide community. We have about 50% academic users, about 50% government users. In any given years, those vary up and down a little bit. We have about 5% of the machine's time going to industry and about 5% going to the international community. And yes, I know that's over 100. They kind of go up and down a little bit each year. The ALCC program is run by the Department of Energy themselves, focuses a lot more on DOE mission work and things that are important in a given year. The images we see here are also simulations done on Mira. These are simulations studying magnetic properties in the sun. And this work is done by folks from the University of Colorado at Boulder. Finally, in our kind of allocation programs, we do some targeted work. One is a program we started about 5 years ago called the Argonne Data Science Program. And this is really us acknowledging that it's no longer just about modeling and simulation on these machines. Instruments like the Advanced Photon Source, CERN, high energy physics experiments in Europe, ITER, the large tokamak coming online. These are all going to generate vast amounts of data and data that needs to be analyzed and can't be analyzed on kind of your standard small cluster. And so ADSP really started to look at how do we support data science at scale on these resources? How do we support machine learning? The early science program, or ESP, is back to that thing I mentioned earlier about getting the community ready for the next generation machines. And right now we are supporting 20 early science projects, 10 of them in the modeling and simulation space across a variety of disciplines, 5 in the machine learning space, and 5 in the data science space. Again, just trying to be aware of time. Just to give you a feel for the 2019 numbers on the system, the top one is Insight. So this represents 60% of the available cycles for those resources. You can see the diversity from biological sciences to chemistry, energy technologies, and physics. You see about 18 million node hours delivered from Theta and 220 million from Mira. Now, again, Theta is a newer machine. Those processors are more powerful. They're about 13 times more powerful than the Mira. So they're both kind of roughly in that 200 million, if you kind of normalized them, space. The bottom one is ALCC program. Again, the same type of diversity in its application space, with the addition of computer science, where some teams were working on codes, underlying infrastructure at scale. The Insight program runs from January to December, and then the ALCC program is offset from that and runs July to June. How is the heat managed? That's a great question. So when I first came to Argonne, we had the old cool Cray, you know, the one that had like the bench seat built into it, and that was liquid cooled. And that was the last machine that was liquid cooled for most of my tenure at the lab. And then when Mira came in 2012, we brought back water cooling. And so every supercomputer that we deploy now, we actually just deployed our first water cooled networking infrastructure. So everything right now is largely water cooled with some air cooling. Now the nice thing about Chicago is we do get a good chunk of free cooling throughout the year. Not that anybody's left their house lately, but it's cold outside, so we do make use of that. So with my time left, I'm going to talk a little bit about science. And again, I'm a computer scientist, so please do not ask me detailed questions about the science that's happening. I'll do my best to kind of allude to what's happening in the various things I show off, but it is not, I am not an expert. Of course, as a supercomputing facility, modeling and simulation has been our bread and butter for years. And as I mentioned earlier, we do see industrial users. So this is actually simulation work done by GE Research, where they were looking at noise of engines and kind of trying to figure out how to lower the noise of engines. This is what I love about my job. I do get to learn a little bit about the science. And so I wouldn't have thought about this. If you make the engines quieter, you actually improve energy efficiency. And so this is a study here around noise and noise turbulence due to the engines. Over the past, actually around Mira time, a little before Mira time, Argonne came to the realization that it isn't just about modeling and sim anymore. Data science has a very important role in high performance computing, as does machine learning, which I'll say in a second. This is actually due to our proximity to the advanced photon source. We started seeing some generation of data there that was challenging to be reconstructed, analyzed in a timely manner with just local resources. Sometimes when you're doing an experiment, you want the answers right then. And so being able to couple these with supercomputers like Theta, like Aurora, allow you to do that. What we're looking at here is actually a reconstruction of a mouse brain. This was imaged at the advanced photon source and then reconstructed in the ALCF. And we're looking at kind of the blood vessels within the brain. Now, this is something that we're really interested in, and we hear about the Brain Initiative. If you want to start to do this and you want to start to do it at scale, you need to look at many different brains. You need fast imaging, like what the advanced photon sources is building out. And then you need resources like ALCF to reconstruct them. And we actually want to get to the point where we're starting to combine this with machine learning to start to try to automatically build wiring diagrams. Machine learning space, we're starting to see a lot of applications of it in science. Specifically here, Rick Stevens, who's the Associate Lab Director for Computing, my boss, leads a program called Cancer in collaboration with a number of other national labs and universities on the National Cancer Institute to look at machine learning applied to analysis of cancer, and more specifically, drug interactions with the cancer and drug interactions with each other, and trying to do this at a scale inside the computer to help narrow the possibilities before they actually start any kind of other experiments. So we have this mod sim, data science, and machine learning kind of driving a lot of our work. I'll wrap up with just a few other example projects. So Dave Baker of the University of Washington has been a longtime user. I tried to denote on these slides too what program these ran in, so you can kind of get a feel for how many hours they use. So this is probably a multi hundreds of millions of core hour type project. In this specific example here, he's working on trying to understand, to try to create proteins that mimic DNA. And really it's kind of a matching problem where he's trying to understand how the various amino acids interact with each other and the resulting 3D protein structure that is formed. Over the years, he's worked on things from everything around proteins, from things like we see here to better understanding its Alzheimer's. So we got a very applied example here. We switched to a more basic science in the work of Salman Habib, who's a cosmologist at Argonne, also the director of Argonne's computational science division. Salman and his team have been working on our resources from day one. He was actually the first person to run officially on Mira, and his group was the last project to officially run on Mira. What they're doing here is they're trying to build synthetic sky surveys. And with that, try to gain understanding from the theories that went into their simulation and connect that to the sky surveys that the telescopes are making today. He's done other work in dark energy and dark matter studies. And their last journey, which was the last big science run on Mira, is one of the largest cosmology simulations done today. Connecting back to experiments, we can look at things like this work out of General Atomics. They host, I think, the last operating tokamak in the United States. They're basically running simulations of the interactions that happen within the sun in this donut-shaped tokamak here. Each shot is, and that's what they call their experiments, each shot lasts some very, very short period of time. And then the whole system resets. It takes about 20 minutes for the system to reset. And in that time, they do their analysis to better inform what they want to do in the next experiment for that user. And they have local clusters associated with it. The data gathering is streamed to them and analyzed to inform that. But it turns out that the amount of sensors and the amount of data that they're collecting now, they can't do that computation within the 20-minute window. So the computation bleeds over into the next run. And so they are kind of off by one. So we started talking to them about how we could actually engage with them. And D3D is in San Diego, California. We streamed the output of the experiment as soon as it's collected to Argonne, compute on it, and send back the results inside that 20-minute window. So we were actually truly informing their next experiment in real time. Not only do we actually compute and send the information back, we did it at a higher resolution than they were able to do on their local resources. And this was a pretty big win for us in the sense that we've got something that's, you know, thousands of miles away, transmitting it in real time, computing on it, and sending the results back. And this is exactly the type of things that, you know, we're also doing in-house with the advanced photon source. Finally, Ken Jansen, another longtime ALCF user at the University of Colorado Boulder. Again, another very applied example here, looking at lift around wings and trying to understand that and simulate it. And this is one of the huge wins on supercomputing. Ken can do many hundreds of different simulations with different parameters, try out different wing designs, try out different physics in the experiment without ever going into a wind tunnel, without ever building a physical model, and do that to inform next step in design. And we're actually seeing, I think even Boeing in their last airplane did it all in the computing. All right, somebody has their hand raised. I can just see questions. I don't know what hand raised. So if you have questions, just type it in the window. I'm happy to answer. So this is just a small example of the type of science that happens on these resources. So I want to just kind of wrap up. These systems do benefit the nation. They do benefit the world. We contribute to science at all levels. From the very basic to the very applied. We see in the background here a simulation of a piston and trying to understand how to make it more fuel efficient. These contributions are brought in across the space. We see things translating into the economy. Industry comes here and does some fundamental research. They come here and try to understand how to make more efficient engines. This is a Pratt & Whitney engineer, one of the early users of ALCF capabilities, to just try to understand their engine design and how to make it more efficient. This benefits Fortune 500 companies. We've had small startup companies from St. Louis come and do material simulations on the systems. And as long as people are willing to talk about doing their science at Argonne and on these resources, again, these cycles are free because the whole community benefits from them. And finally, and I'm happy to take questions here at the end, our education and outreach. Argonne itself has a tremendous program in outreach. Here we have some young, but I hope to be computer scientists someday, that were part of the Introduce a Girl to Engineering Day, which brought a couple hundred middle school aged girls to the lab to learn about all kinds of science and engineering happening at the lab. We do this every year. We have, as I said, 100, 150 grads and undergrads come every summer just to work in computing alone. Argonne takes very seriously getting people excited about science, giving people the opportunity to experience. So we have a great education and outreach program. And with that, I think I probably ran a little bit over. I'd like to thank you for your time. Apologize for Mr. Loki barking a little bit, but with that, I'll take questions.
Great, thank you very much, Michael, in talking about what's coming up next with Aurora. So I know in the interest of time, so I'm just putting a poll here, so you have a chance to please answer answer our questions here for feedback on the poll. With that, we'll open the Q&A session. We have lots of questions. I'm going to ask Gina Martinez, our Vice Chair of IEEE Computer Society Chicago, to moderate the questions. So Gina.
Yeah, thanks, Alvin. So our first question says that, can you summarize the difference between Knight's Landing and Broadwell cores?
Knight's Landing and
Broadwell.
Knight's Landing was a experiment with the Xeon Phi processor. So these were processors that had a larger number of cores and a smaller computational power. So you see, like, the processor in Theta is a Knight's Landing, and 64 cores per processor. Don't quote me on this. Broadwell is a line of Xeon processors, correct? Oh, so I assume it's an x86 heavy Xeon processor. So the cores are going to be a little more capable, probably a smaller number count, and probably some slightly modifications in instruction sets. So I know that our Knight's Landing have some instruction sets typically not found in the Xeon, but largely in kind of their focus between large heavyweight cores and smaller many cores.
Thank you, Mike. So our next question, what do you lose by retiring such a machine such as Mira with IBM's unique interconnect? Will newer machines be as good as Mira for data sharing between nodes intensive applications? And will some of their raw core horsepower be wasted waiting because of the differing interconnect strategies?
Wow, these are good questions. So Mira was unique. And so, and for that, because it was unique, there were challenges, right? So it was part of this blue gene line of systems from Intel. It kind of spanned the space between Intel's research computing and a product. I mean, there were a couple hundred of them deployed. The 5D Taurus was extremely fast. It built dedicated, isolated network links between each processor for each job. And so you didn't get that contention and noise on the backbone. So yeah, we're not going to see another machine like Mira in kind of the general purpose space. And, just like, with commodity hardware that you buy at Best Buy, right? You make a choice. If you want to build your own special custom gaming system, you build it from components and you put everything exactly the way, but it requires your time in that. And so the same thing kind of holds. I mean, we're buying things more off the shelf from the vendors now. And while they push the technology and things like Cray Slingshot, our advances in interconnects, they're trying to hit the broadest user base possible. And so we do see contention on the back plane, communicating from one processor to the next. Yes, we give up somebody has to wait. So it does, you do lose out some on the processing capabilities. It's all kind of a trade-off. And, and we're constantly working, and I'm lucky to have a great team looking at ways to try to mitigate that.
Thank you, Mike. So our next question, what impact do you think will be made on supercomputer designs by trends in semiconductors? For example, a fading Intel, NVIDIA-owned ARM, or the evolving world of RISC-V?
Ooh. That's a good question. So I think we're very much interested in what happens with NVIDIA and ARM. I don't know if the sale's gone through or if it's, but what I think that gives NVIDIA, access to their existing GPU designs and integration with a very flexible ARM processor that's a very interesting future there. RISC-V is also, again, interesting things. We see that in other systems popping up. Intel's our partner, so we're extremely excited by all the work that they're doing, both in the now new discrete GPUs, the Ponte Vecchio system, where they're going with the Sapphire Rapids processors. The community as a whole has something to be nervous about. I mean, I think just it's in the press about challenges as we, go to smaller and smaller fab facilities. We have some interesting times ahead of us. I'll leave it at that.
Thank you, Mike. Our next question, what prevents a machine, particularly one as successful as Mira, from continuing operating?
I would say it's kind of a cache floor space trade-off, right? So I could almost guarantee that we'd be running Mira today with, after some point we were maybe using and losing one node card or so a month for a machine that was 7 years old at its retirement. That's to be expected. Of course, we had plenty of spares. And so one is the floor space. It was 48 cabinets, the size of fairly large refrigerators. So I needed the floor space. And then as we saw kind of in that one chart, its power was probably double that of Theta's. And so we're talking about significant electric bills. And so those kind of trade-offs come into play, making room for the next machine.
Thank you very much. Our next question, how much compute time and power is needed to train large data models?
That's a pretty broad question. I talked to the machine, if I talk to Rick, they don't have enough time on the systems as is to train their models. And that's just because they're constantly exploring. So yeah, I don't have a good answer to that question. I know they're making extensive use of the DGX-3s. They'll take a full node, which is eight A100 NVIDIA systems. They'll run, they've been running on those, working on COVID problems pretty much exclusively since we got them in kind of, when did we get those? We got them kind of March, all of the rest of them in March. So they're making use of them all the time. And they've really just been really focused on problems around COVID and machine learning.
Thank you. Our next question is ALCF considering continuing virtual internship options for students through the 2021-2022 academic year?
Absolutely. Absolutely.
Thank
So
you.
So look in January timeframe, the things will start coming up on the website. You just search education and Argonne, you'll get to our education pages, and the internships should start opening up then.
Thank you. Our next question, is ALCF utilizing SPAC in preparation for Aurora?
Yes. Yes, we are using SPAC. So parallel to the computing facilities, Argonne and Oak Ridge, there's a huge project called the Exascale Computing Project, also run out of DOE's computing area. And it's led by Doug Cothy, and it's 5-7 year project that has application work, software work. It had about, don't quote me on this, I don't know if it was $300 million or $500 million of partnerships with industry, and SPAC is a huge portion of that. Not funding wise, but effort. in packaging software for exascale systems. And so, yeah, we are moving towards SPAC. I just never thought I'd heard the word SPAC outside of the small group that's working on the exascale computing project. So I was surprised.
Thank you. This one appears to be our last question in the Q&A. What does a carbon-free supercomputer behave like?
Oh, I don't know. We don't have a carbon-free a supercomputer. There's been times when we've spent a lot of effort thinking about, and I assume this is about the carbon footprint associated with supercomputing and the vast amount of power and heat power they consume and heat they generate. And technology has not kept up with that, right? So the vendors have not been incentivized to really look in that space. There's a lot of interesting startups and innovative things happening in research labs, but nothing that I know of at scale. And so we make use of, our climate and free cool as much as we can. I think there's a lot of work there. I mean, I think we start power capping the systems. There's interesting work to be done research-wise in terms of understanding the power profiles of individual applications, rolling those power profiles into your scheduling algorithms such that you can co-schedule power consuming applications and less power consuming applications, shifting the power consuming applications to running at night when power is cheaper. There's a lot of work that can be done in that space.
Thank you. All right, Alvin, you said, we do have a question from the chat from Bruce. Can you show a simple architecture of one of ECAFLAP machines?
So I don't actually think the ECAFLAP machine looks that much different than existing systems. I mean, I don't have a picture to show you easily. It's built up a lot of the same ways that our existing machines are built up of their nodes, and these nodes are pretty beefy nodes. I mean, so the Aurora nodes will be 2 Sapphire Rapids, 6 Ponte Vecchio GPUs. There'll be a hierarchy of memory from kind of your very close to the GPU high bandwidth memory to your kind of traditional RAM type memory to SSDs to spinning disks and the like. They're connected, interconnect is this new Cray slingshot technology, kind of wired up in the Dragonfly topology. We heard some questions earlier about the challenges that come with that. So it looks a lot like the systems that we have on the floors today, just at a different scale and more hierarchy and heterogeneous components within each individual node.
Thank you. We'll just ask the 2 questions remaining in the Q&A, and in the interest of time, and we'd hate to keep Mike too long here, we'll just ask this will be the 2 questions we'll address. So the next question, what can be done to speed up codes if we reach the end of Moore's law?
Well, codes can be more efficient, right? So, I'm not sure I should say this out loud. It's a lot easier to buy faster hardware and run the same code on it and see a performance increase. It's a lot harder and a lot more work to get in and tune a code. But doing so, you can actually eke out more performance than is there. And we're seeing this, right? So I think as we see our code base move from traditional CPUs to GPUs, people have to get back into their code and move it to that platform. And in doing so, they often see, optimizations that they can make that even when they come back to CPUs, their codes run faster. So there's a lot of work that can be done in tuning code, but that is a time-consuming, human in the loop process, which tends to be costly. So there's a challenge there. I mean, I think there's interesting research work happening in the space of, programming and machine learning, and trying to get machine learning to write more efficient code. So you could actually see if that would be a possibility. We could see hardware being designed specifically for specific algorithms to accelerate them. And so you could even see more of a mixing of processor types to try to eke out performance. Other things that come to mind.
Thank you very much. So our last question, do you see future supercomputers at the leading edge of high-end CPUs and interconnects, or will the future roadmap for the biggest supercomputers be dominated by a proliferation of cheaper nodes and less exotic interconnects in huge volume, wasting some cycles to save power, floor space, and dollars?
Yes, I do think people will go in that direction. But there will be people that will go in the other direction. So I think there'll be a bit of both. I do think this notion of cheap low-end power processors in huge numbers is an interesting approach for a class of problems too, right? So the other thing I would say in kind of that question is different problems map different application spaces, different domains, implementations of the code map differently to different hardware. And so I think people will start being more aware of their codes and where they're deployed and try to deploy them in the most appropriate spaces.
Okay, great. Well, thank you very much. I know we are out of time and we could keep going on, but of course we have to continue with the rest of what we are doing. So I'm just gonna just share my screen to tell you the next talk that we have. So let me just quickly share my screen here. Okay, so our next talk is on Wednesday, and this is going to be our last talk for ACM Chicago, for IEEE Computer Society Chicago, and also IEEE Vehicle Technology Society Chicago. So it's a 3-chapter joint event. So I will be giving a talk on machine learning for connected vehicles, part of my work that I've done with BMW Technology Corporation. The tech office for BMW. And so that's on Wednesday at 6 p.m. Chicago time. If you want to register, just go to the bit.ly link that's there. And you also see this too as well in the email address too as well, in your email. So anyway, yes, so thank you everyone for attending this evening. Like I said earlier, this webinar was recorded. So the recording, the slides, as well as the next talk on Wednesday will be emailed to you. For those who are collecting professional development hour credits, I know there's some people that are doing so. You will also receive a link to getting that certificate where you can enter your name and you can claim that for professional development hours then. All right, so on behalf of everybody here, IEEE Chicago, ACM Chicago, and Mid-America Club and SWE, thank you everyone for attending this evening. Very, very interesting talk by Michael. And everyone, happy holidays and continue to stay healthy and safe. Thank you for attending.
Thanks.
Thank you, Michael.
Michael, thank you, Alvin.
Okay, thank you.
Thank you, Renee.
Bye.